In this lecture, we talk about projective space. So 5.3, projective space. And so honestly, I just love projective geometry. That's why I want to talk about it. And it gives us some interesting examples of groups. And also definitely it will appear in the next quarter and so on. So at first this might be a little bit complicated, but I guess you will get used to it. And one of the online classes will be devoted to getting intuition about projective space. So let me start with definition. So definition. At first it might sound like it's a part of linear algebra, but actually it's not. So let V be a vector space over some field, over F. And then projective space, which is usually denoted P of V, is the set of lines in V. So lines are just subspaces of dimension 1. Okay, so there are two questions. What does that mean? Why do we care? So the main idea is that there are lots of different ideas here. Let me maybe start with drawing a few pictures. So if V is just n-dimensional vector space, Fn, then this projective space is also denoted by Pn-1. Sometimes you write F here, sometimes not. Okay, so I know that's absolutely not intuitive, so let's start looking at first examples. So let's start with the most familiar example. We just take F being to R and n equal to 2. And then what we get is what we will call P1, and that's called projective line. So how to think about it? So that's a fairly typical mathematical question when you have some objects, and in this case, let's imagine we have a usual coordinate system, and we are just trying to parameterize all lines passing through the origin. And you want mathematically to parameterize some objects. How you would do that? So that's something from high school. So you know that lines like that are parameterized by equation y equal to kx. And so basically every line corresponds to one parameter k. So you might think that P1 of F is just, in this case R is just R. Because clearly every line is parameterized by its coefficient, and this coefficient determines it uniquely, so probably projective line, it is just a usual line. But that's not quite right, because there is exactly one line in this picture which doesn't fit, and this is this one. So if you take the vertical line, it's not a graph of a function in this calculus sense, it corresponds to k being growing to infinity. So you need to add one more line, which I will denote by kind of infinity. And you can think of it as given by equation y equal to infinity times x, or of course, much more reasonably, x equal to 0. So projective line over R is a union of the set of all points in R plus one infinitely far away point. So here is another way to see the same picture from a slightly different perspective. You can just look at all lines passing through the origin. And suppose you want to parameterize them. I mean, it's the same parameterization, just in different coordinates. You can choose additional line. Let's say in this picture it will be a line x equal to 1. And then you can just intersect every line passing through the origin with this x. So actually this will be exactly point k. And then you get identification from set of lines, which is just by definition this P1, you get that it is in bijection with points of this line, let me call it big L, of L union with one more point. Okay, so that's how that's what P1R looks like. Of course, from here it's absolutely not obvious why we are interested in that, but it will become clear later. So before that, let me explain maybe in a few words. So that generalizes. So if you have arbitrary f is any field, then you can form P1F. That's projective line over F. And arguing in the same way, so of course it will be slightly more abstract, you will, but you can still do the same thing. You can say you have coordinates x, y, and every one-dimensional subspace in two-dimensional space F2 is now given by a linear equation, and you can think of it as equation, let's say, so every line is given by equation ax plus by and equal to 0. That's equation of every line. And then basically you can identify P1F with F union with infinity, where, I mean, if you want to parameterize all equations, then most of them will parameterize by coefficient a divided by b, except that there is just one which doesn't fit there, where b equal to 0, and so there is one more point, equation x equal to 0 corresponding to this infinite point. So this is how you can think about projective line, just usual points of a field plus 1 point. And that's not an algebraic structure. You cannot add points on projective line. You cannot multiply them in such a crude way. But it's more kind of a space. It's something which is more like a space. And the more you go into math, the more you understand that working with this projective line and projective space is so much more comfortable, convenient, and interesting than working with the usual kind of Rn space. It just behaves better in so many different ways. But on the other hand, it's more complicated as well. So let's maybe look at some other examples. So what can I say about P2 of F? So P2 of F, that starts to be even trickier, because now we are looking at lines in 3D. So you take 3D, R3, and then you look at all lines through the origin. So they form this kind of a pattern, and then you can do absolutely the same thing. You can take a plane not passing through the origin, intersect every line with it, and you will get that most lines are just parameterized by these points of this plane. So P2 of F is basically, from this perspective, also looking like points of the plane. But again, there are additional points. Here they came from the line which was parallel to your line, you cannot intersect it. And here it will come from all lines parallel to your plane, which you cannot intersect with it. And this will be just lines through the origin in one particular plane. And so you basically need to add previous picture. So you see it starts to look kind of complicated, but you can think that you have sort of so you have usual points. These are kind of usual points, and these are infinitely far away points. And the way you can visualize that is you take usual plane and you think of this part as being just usual points, usual lines here. And then if you have two lines which are parallel to each other, then you think of them as kind of passing through one additional point. And this point corresponds to kind of the direction where all these lines go. And so this P2 of F is just usual plane plus a collection of points where each point kind of points towards one direction where parallel lines kind of look at. Formally speaking, you can just say that you add classes of equivalence of lines with respect to relation being parallel. So that's a whole additional topic. Please look into it, research it. and it will definitely appear a lot if you continue studying math. So I want now to switch attention to this very familiar case of finite fields. But before that, I want to talk a little bit about symmetries of projective space. So the reason why people like projective space so much is because it is a much more symmetric object than the usual space. So let me try to convince you of that. Okay, so let's again look at a vector space V. So V is a vector space over F. Space over F. So what are symmetries of V? Symmetries of V. So what are symmetries of V? I mean, of course, that depends on what structure you put there, but you can say, okay, so symmetries of V are linear transformations, and we have this group GL of V, and if I imagine that's just Fn, this will be GLN. So we already discussed that. That's a group of symmetries. Okay, what is the dimension of this group? So I don't want to define dimension here, but like let's just count parameters. I mean, if you want to pick an element of GLN, that's fairly simple. You just need to pick a basis in V. And then you will have a standard basis, your basis, and you just need, it's just the number of matrices basically. Except there is this condition determinant is non-zero, but that condition doesn't change much. So that's just n squared. Okay, so that's okay. So basically if V is a plane, then it has this four-dimensional 4D group of symmetries. And if you take V being, I don't know, space, then you have 9D symmetries. So, highly symmetric object. But on the other hand, let's look at this projective space. So, first observation is that GL of V acts on the set of lines. So the set of lines is a P of V projective space. And again, so in more concrete terms, it will be GLN acts on Pn minus 1. So GL of V acts on Pn minus 1. So why? Because linear transformation sends lines to lines, subspaces to subspaces, lines to lines. So it sends it acts on Pn minus 1. Okay, so let's maybe look, before even doing anything more fancy, let's just look what this looks like. So for this I want to introduce some coordinates. So how to coordinatize this space? So what are coordinates on Pn minus 1? Just suppose you want to somehow determine each point. So Pn minus 1, I mean Pn minus 1 is a set of lines. And these are just, I mean, lines are solutions. So solutions of one linear equation. And oh, sorry, let me do it differently. So what is a line? So every line is a one-dimensional subspace, so you can take a vector along the subspace. So set of lines is just the same as set of, I need to say non-zero vectors, because any non-zero vector determines a line of non-zero vectors in V. And then I take equivalence relation on them, so modulo the equivalence relation, where V1 is equivalent to V2 if there exists some lambda such that V1 equals lambda V2. So set of non-zero vectors in V such that two vectors are equivalent if they are proportional. Okay, so basically, another way you can say is that set of non-zero vectors is just Fn. Then you subtract 0 as a vector. So you just take away this 0 vector. And then you identify vector with coordinates x1, xn. It's just the same as vector with coordinates lambda x1 and so on, lambda xn. Where lambda is anything which is not equal to 0. So this is how you can think of your projective space pretty concretely. So again, that's an object which is a kind of class of equivalence type. So usually people use homogeneous coordinates. So homogeneous coordinates are like this. So if you want to determine this point, you introduce coordinates where you put in brackets x1 double dot, x2 double dot, and so on. And you should think of it as like a long proportion, 1 proportional to 2 proportional to 3, and so on. And this coordinate is the name, it's class of equivalence of vectors x1 and so on, xn, where not all xi are equal to 0. So this is what our lines look like. So you just can think of them as basically this kind of sets of numbers up to proportionality. So for instance, if you take, let's say, P2 of R, then if you want to parameterize lines, you can just parameterize them as, so this is lines in R3, and these are basically, you can take, for instance, a line 1, 2, 3, and this is basically, this is a linear span of a vector 1, 2, 3. And that's absolutely the same as line 2, 4, 6. The same as line -1, -2, -3. So that's how you think about it. And from this perspective, if you just think of your points being these vectors up to proportionality, it's really simple to say when how this GLN acts on them, because I mean that's pretty clear. Let's look at that. So in coordinates, you can take just GLN, some element in GLN being some matrix. And this will be like this long n by n matrix where I have this A11, ANN. And if you just want to take this A and kind of act by it on a point x1 double dot xn, so what you do, you just, take this vector and multiply it on a matrix. So you just see what matrix does to this particular vector. And in this way, you get basically, you will have this linear function in each term. So you will get A11 x1 plus A1n xn double dot AN1 x1 plus ANN xn. So this is what an action looks like. And you should remember that we consider these vectors up to proportionality and these vectors up to proportionality. For instance, if you take 1 to 3 and if you act by some matrix like 0, 1, 0, 1, 0, 0, 0, 0, 1 on your kind of point 1, 2, 3, then you get point 2, 1, 3, and that's again the same as point 4, 2, 6. So that's how it looks like in coordinates. By the way, these homogeneous coordinates give another way to think about P1. So you can take P1 now of F, and in coordinates this will be just this F2 without 0, 0, factored over where you identify points xy with lambda x, lambda y. And so basically what you can do, so if you just think about these points x double dot y, we use this homogeneous notation, you can divide them in two classes. You can look at points where y is not equal to 0, and then this pair becomes just a pair x divided by y 1. You can just divide by y and normalize it. And this is what we identified with just points of f. And then there is one more thing where you have y equal to 0, so you have some x and then 0. And then since it's not 0 because you cut away the origin, it's the same as 1, 0. And so that's one additional point and you call this infinity. So that's basically what the previous picture told us, and you can easily see it in homogeneous coordinates. Nice. So far I said maybe nothing very interesting, but now let's look at some more details. So I want to understand how symmetric is my projective space. What is the group of symmetries? Okay, so as we already discussed, this GLN acts on Pn minus 1. And then there is one kind of subtlety here. And the subtlety is that in GLN there is this particular matrix lambda, 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 lambda 0, where lambda is non-zero. And if you look at any such matrix, so this one acts trivially. And the reason is very simple, because if you take a homogeneous point, x1 to the xn, which represents for you, so I remind you that's a line through vector x1, xn, and then you take this point and apply this matrix, then you will, and this is, let me call it lambda times identity, and if you take lambda times identity applied to this point x1 double dot xn, you will get, of course, a point lambda x1 lambda xn, but in projective world that's the same as point x1 to xn. So basically nothing changed. So this thing, which I remind you, that's nothing but, so this is just a center of GLN. So these are matrices which commute with everything. So center of GLN, that center, these are also called scalar matrices. Scalar matrices fix all lines. And so in some sense, looking how GLN acts on the space is a little bit of an overkill. You don't care how these guys act. So what we do, we factor. So definition, projective linear group PGLN is a factor group GLN or this center or scalar matrices. And remember, I already even defined that because I said that, look, there is a center of matrices and it's a normal subgroup. And normal subgroups are interesting, so let's factor over if we get something. And I said that these are matrices up to proportionality. And the question is, why do we care? And the reason is because this group naturally acts on Pn minus 1. So PGLN acts on Pn minus 1. And these are called projective transformations. And what is very important is that if you look at the dimension of this PGLN, of course, we can count it. So roughly, I mean, how many parameters we have? So basically, we just take, dimension of GLN, which was n squared, and then we just kill one parameter. We factored over one-dimensional subgroup. All these dimension words, this is completely vague. I have not defined it or anything, but you need this number of parameters to give an element there. And you might say, okay, so why did I say that projective space is so much more symmetric than usual space? Because it looks like it's smaller. But this is much bigger than if you actually, so projective space Pn minus 1, you think of it as Fn minus 1 plus additional points. And so n squared minus 1, and then you compare it with n minus 1 squared, and that's much bigger. So the thing is that if you actually think of your plane and compare symmetries of your plane with symmetries of lines through the origin in the plane, that's, of course, plane is more symmetric object. But if you compare plane with a set of lines in 3D, which looks like a plane plus something else, space of lines in 3D is much more symmetric object than a set of points in the plane. Sorry, than the plane. So that's why people like this projective transformations so much. And then I can tell you what they do. So let's kind of look at the particular case of P1 over real numbers or complex numbers. So if you just look at the simplest example, so what is PGL2 of F acting on P1 of F? So definitely we think of this as, you know, equivalence class of matrix A, B, C, D, and equivalence, like, it's equivalent to lambda A, lambda B, lambda C, lambda D. And then you want to act, and remember, so we act on these homogeneous points, x, y, and the rule is just take a matrix and act, and you get this ax plus by, cx plus dy. And we know determinant is not 0. ad minus bc is not 0. So this is what it does, and nothing so far happened, that's just by definition. But then remember, we like to identify P1 of F with F plus infinity. And in some sense, when you do calculus, you know that, I mean, you have seen infinities already. So infinity is kind of, I mean, you can sort of ignore it, it's just something very big. I mean, of course, we cannot do it there, but here, but still, main part of projective line is still this. So let's look what it does to these points. And remember, for this, we just look, so if y is not equal to 0, then we can say that this point x, y is just the same as x over y1. And let me call this t. So now you can think of t as coordinate on the projective line, and it can have this value maybe infinity, so y equal to 0, you think of this t being kind of infinity. That's this coordinate here. And then in this coordinate, our matrix A, B, C, D, kind of acting on the variable t, will do the following. So you just look at the point ax plus by, cx plus dy. And in terms of, to rewrite it in terms of t, first let's just divide by cx plus dy. So again, it might be 0, so it's not exactly kind of well-defined thing, but let's do it for at least for the time being. And then we can divide by y. So, and then you get that this is kind of a t plus b, ct plus d, 1. And so in coordinate t, you can say that you have a map from f to f, which is just takes t to at plus b divided by ct plus d. And except there is one detail, this map is not always well defined. You have additional point infinity, and you have to say where it goes, and of course you do kind of limit, you get b over d. And also there is maybe one point where denominator is not defined, it's minus d over c, and you say that it goes to infinity. And that's how you define this projective transformation. So basically, PGL2 of F are just these transformations which are just fractional linear. So these are fractional linear transformations. Fractional linear transformations. So that's the main idea. So of course, if you just look at linear transformations of F to F, which I don't know, rescale it or even shift it, so comparing usual linear transformation, which will be just AT plus B, with all fractional linear transformations, I mean, this is such a richer group. And this is exactly what PGL2 looks like. And by the way, you can see here that if you rescale A, B, C, and D, you get the same element, and that's because these two matrices are the same. Okay, So you can check in some other way that fractional linear transformations form a group under composition, and this will be exactly the group PGL2. Okay, so in the next lecture, I'm going to look at sort of how transitively PGLN acts on lines and derive consequences about PGL2 over finite fields.